Let's recall the requirements that mathematical model puts on the physical process that it describes. First, the continuum of states. Second, the true randomness. And third, the interference. We just have seen that continuum of states in the form of unitary circle is required, but we can easily implement it without any notion of quantum mechanics. What about the second one, the true randomness? Randomness is often underestimated when it comes to the power of quantum computing. Everyone can think of himself as a perfect randomness generator. You just need a fair coin. For example, heads we encode as 0 and tails as 1. You throw it, catch, and see the value. It's heads in my case. So this is the value of your random bit. But it appears that this random bit is not truly random. In classical mechanics, all you need to predict its value is to measure all the initial parameters of the throw with a sufficient accuracy. And even if you don't know these initial parameters, the system itself knows them. By the word system, here I denote everything which can alter the throw, like the coin itself, your body, air at the room, etc. So even if for you the result of this throw looks random, it is not really random for the universe. The universe can predict it. And for quantum computing, we need such randomness that cannot principally be predicted. First of all, is this type of true randomness even possible? Because for us humans, this thing, the real, true randomness, seems very unnatural and counterintuitive. Our mind is organized to believe that every event has a reason. We tend to think that the world is maybe not yet well understood, but in some sense deterministic. But for now, theoretical physicists all agree that there is such thing as true randomness. To demonstrate it, we would need an experiment described on this picture. It is called the Young's double-slit experiment. The British scientist Thomas Young designed this experimental set to explore the wave nature of light in 1801. The principal part of the set is this screen with two closely situated narrow slits in it. The source here emits something in the direction of that screen. In the case of Young, it was light, but we are going to throw electrons from this source. Why electrons? Well, because most people imagine an electron as a small ball. There's even such thing as an electron radius, though it's not known yet. Anyway, very small. So we are going to attack this screen with two slits by throwing small balls in it. And after the slits, we are going to place two detectors, which will give us a loud click when an electron hits the detector. And we are going to register which detector was hit. So we will fire electrons one by one and see what happens. First, if we manage to do this experiment correctly, we will find out that there are three types of experiment outcome for each electron. The first one, electron hits the detector 1. Second, electron hits the detector 2. And the third outcome, electron does not hit any detector. The third outcome means that the electron did not pass through the slits and were stopped by the screen. We are going to exclude those outcomes from our consideration. And regarding the first two outcomes, they are going to be completely random. there's no way to predict which detector is going to be hit by the next electron. Physicists tell us that this set is a source of the true randomness. To predict the outcome, we need to measure both the position and the momentum of the electron in the start of its journey. But we can't do it because of the Heisenberg's uncertainty principle. If we know the position, then we have some uncertainty about the momentum. And it is not because our measurement process is not perfect. It is because the momentum of the electron, in this case, is not well defined. And even the universe itself does not know it. So the universe itself cannot predict where the electron will go and which detector it is going to hit. This true randomness is not at all like the usual randomness we experience in our everyday life. We used to think about randomness as of some lack of information. Something seems to us random, but we believe that if we just had more information, then we could certainly predict the outcome. It is really hard to imagine the real randomness when the outcome cannot be predicted with all information being available. But we can try. Imagine that we have two identical universes where this experiment takes place. In the first one, electrons takes the upper way and hits the upper detector, while in the second set, electron takes the lower way and hits the lower detector. Now, the most important part. Since these universes are completely identical at the start of the experiment, there are two identical you observing the result there. The first you see the upper detector was hit, while the second you see the lower detector was hit. Until that happens, both these persons, both you, were completely identical. But after that, you are not anymore, since you will not agree on the fact which detector was hit. So, instead of the notion of randomness, we use this. The electron does not randomly choose its way. It always takes both ways, but in the different universes. There is no randomness at all, but for you, subjectively, the result appears to be random. Because you cannot be both these persons on the picture simultaneously. Before the experiment, you could, since these persons and everything around them were identical. But now, it is not. You observe the random result, but different for different you.